Hello everybody, and welcome to this series in brachytherapy. Today we will be talking about ICRU 38, which is titled Recommended Dose and Volume Specification for Reporting Intracavitary Brachytherapy. And so the objective of this talk, essentially, we will follow the table of content of this report. I will give succinctly a good overall summary of the report, and we will start first by defining some of the common terms and concepts that are used in this report, and then the second part of this discussion, we will essentially zoom in to look at the recommended parameters for reporting absorbed dose and volumes in intracavitary brachytherapy. And so the scope of ICRU, essentially the primary objective of the International Commission on Radiation Units and Measurement is to develop internationally acceptable recommendations regarding three important aspects. The very first is the physical quantities and units of radiation and radioactivity. The second essentially is to recommend procedures that are suitable for the measurement and application of these quantities in clinical radiology and radiobiology. And lastly, to provide a complete set of data required in the application of these procedures for use, and with the intention, of promoting or ensuring uniformity in reporting across different centers. And so, to provide a brief historic timeline, prior to the publication of Report 38 in 1985, in 1978, Report 29 was released. And the objective of Report 29 was to provide recommendations for dose specification for reporting external beam radiation, therapy with photons and electrons. Then in 1985, Report 38 was released, which was meant to provide recommendations for dose and volume specifications for reporting in intracavitary brachytherapy in gynecological cases. And then after 38, in 1997, 58 was then released, which was meant to provide recommendations for dose and volume specification for reporting in interstitial brachytherapy. After 58 came 89. But the subject of discussion today is ICRU 38. And so what then is the central tenet or the central purpose of this report? The report essentially deals with the problem of volume of dose and volume specification for reporting intracavitary brachytherapy, and therefore the central or the primary subject is dose and volume specification for intracavitary treatment of cervical carcinoma. However, what we need to keep note is that the concepts and the recommendations proposed here can be applied in other intracavitary brachytherapy applications, as you will later on see. Now, in the introductory aspect of this report, they actually mention the fact that typically intracavitary brachytherapy is often administered as a boost after external beam radiation therapy. Therefore, it is desired that we maintain the definitions of quantities like target volume, treatment volume, irradiated volume as defined in external beam radiation therapy. But it is also noted in this report that unlike external beam radiation therapy, in which the dose is specified at a reference point or a set of reference points, it is stated here that the dose specification in intracavitary brachytherapy is really not meaningful when specified in terms of the absorbed dose at reference points because of the high dose gradient or dose distribution around a brachytherapy source, as you can clearly see on the graph. Now, the rationale for the publication or the development of this report was due to the fact that at the time, radon or radium was being progressively replaced by gamma emitting sources such as cesium-137, iridium-192, and cobalt-60. Now, we will talk about briefly why in a little bit. And secondly, this new set of sources that were available were not the old dosimetric system really was not very helpful in determining the dose distributions with the use of these new sources. And lastly, unlike the historic unit that was currently being used at the time, milligram hours of radium, several centers around the world had started, using the SI units more widely, and so they felt there was a need, to provide a standard set of recommendations to ensure uniformity in reporting across different centers. And so the definition of some common terms and concepts stated in this report, the very first that the report talks about are radium substitute. Historically, radium was the only available radionuclide that was being used with known characteristics and properties. And so a typical radium tube was between 1.5 cm to about 2.5 cm in length and contained between 5 milligrams to up to about 20 milligrams of radium. Now, one of the things that the disadvantage of radium was that one of its byproduct, radon, was a gas and could easily leak and contaminate or even and expose the staff to radiation. And so new sources were being produced at the time, such as cesium-137, which are essentially similar in size and shape to radium, with a similar output, but with little to no contamination from leakage. And so the availability of these sources actually provided a radio protection advantage as compared to radium. Now, when we look at sources like iridium-192 and cobalt-60, what was particularly interesting and advantageous to these sources was the fact that they had little to or no contamination as compared to radium, but in addition to that, they had a very high specific activity. Because of the very high specific activity, these sources could be miniaturized or made to be very small, and because of the small size, the application of these sources was a lot more convenient and easy as compared to the bulky radium or radium tubes that was used. And then this report essentially talks about the simulation of linear sources. And so in modern application or devices such as the remote afterloader, linear sources can be simulated in one or two ways. It can be simulated as a set of point sources or as a moving point source. And the moving point source can either be stepwise, oscillatory, or continuous. Now, the set of point sources may have equal activities and equally spaced in order to produce a uniform linear activity or uniform linear points or uniform linear source, or the set of point sources could have unequal activities and unequally spaced in order to provide an improved dose distribution to cover the target to the desired level by the authorized personnel. And so 38 essentially talks about dose rate and describes dose rate in three fundamental categories. You have low dose rate, you have intermediate or medium dose rate, and you have high dose rate. Now, low dose rate is defined as, between 0.4 gray per hour to 2 gray per hour. Intermediate or medium dose rate is defined as 2 gray per hour to 12 gray per hour, and high dose rate is defined as any dose rate greater than 12 gray per hour. Now, with regards to the after loader techniques, by replacing radium-226 with gamma emitting sources of lower energies implied that better shielding could be provided. There was less contamination, as well as the protection of the radiation exposure of staff to radiation was essentially reduced to a minimum or to near zero. And also, after loading techniques or devices provided better positioning, improved dose distribution, as well as a shorter treatment times, especially when sources of high specific activities were used. And so 38 talks about 3 dosimetric systems that we are going to talk about here. You have the Stockholm system, the Paris, and the Manchester system. But essentially, what is a dosimetric system? A dosimetric system are a set of rules designed to deliver a defined or prescribed dose to a pre-designated region, typically the target volume. Now, prior to the development of computerized treatment planning techniques, there were several classical implant systems that were developed to calculate for a given target volume the total number of activities of the source, the number of sources, and the dose distribution within the target. Now, one of the things that I would like to also mention here is the fact that each system, as we will describe after this, is specific to a particular radioisotope, as well as its spatial distribution within the applicator. And so every dosimetric system is described in terms of the source strength, the geometry, in other words, the distribution of the source within the target volume, the method of application, as well as the specific isotope and its spatial distribution within the target. And so we have fundamentally 3 dosimetric systems as described in this report. You have the Manchester system, which is derived from the Paris system, which is essentially different from the Stockholm system in the way it is applied and in the distribution of the sources within the applicator. Now, before we move on, each system typically specifies 1, the type of radioisotope to be used. In this particular case, we'll talk about radium. 2, the geometric arrangement of the radioactive isotope within the applicator. And 3, it gives explicit details or specific details of the treatment, including the dose, the application time, as well as the administration. And so let's begin by looking at the Stockholm system. Now, as we begin to discuss this, I would like for you to keep track of how the applicator is designed, both the intrauterine tube as well as the vagina applicators, the amount of radium or the specific dose of radium used in both the intrauterine tube as well as the vagina applicator. The fundamental question is, are they the same or different, and why? How many radium tubes makes up the intrauterine tube? And also, how many applications are given? Is it 1 application, 2 applications, or more? Now, for the Stockholm system for intracavitary implants, 1, it was introduced by Costa Ferrell and a couple of other folks, and it was based on the fractionated course of delivery using radium-226 over a period of 1 month with 2 or 3 applications. Now, each application lasted for about 20 to 30 hours and separated by a period of about 1 week. So there were 2 applicators used here: a flexible intrauterine tube that consisted of 2 radium tubes that was loaded with about 3 to 90 milligrams of radium, and then it also had a vaginal applicator, or a form of a box that contained about 60 to 80 milligrams of radium. So you could clearly see this is our intrauterine tube, and this is our vaginal applicator, which was in the form of a box that was placed, close up to the cervical os. What you need to keep in mind is the fact that the loading was unequal in the uterine and in the vaginal applicators, and typically the total dose of 6,500 to 7,100 milligram radium was prescribed for the intrauterine tubes, as well as 4,500 milligram radium was prescribed for the vaginal applicators. Now, the Paris system was essentially different from the Stockholm system. One, in the number of applications that was used. 2, the design of the intrauterine tube and the vagina applicators. Now, if you look at the Stockholm system, the vagina applicator was in the form of a box that was placed close up to the cervical os, and the intrauterine tube had 2 radium tubes that was being loaded with between 30 to 90 milligrams of radium. But when you look at the Paris system, it had 1 intrauterine tubes that had 3 radium tubes. Now, instead of a box that was placed up close to the cervical os, we had 2 colpostats, A and B, that was placed in the 2 vagina furnaces, and 1 that was placed right in front of the cervical os. Now, unlike the Stockholm system, in which they gave 2 or 3 applications, and each application separated by about a period of 1 week, the Paris system had a single application of radium with a treatment time of about 120 hours, or typically 5 to 8 days. Now, the dose in the Stockholm system was unequally divided, but the dose in the Paris system was equally divided. And so these were the fundamental differences between the Stockholm system and the Paris system. Now, the Manchester system was derived, or is derived, from the Paris system. And so if you look at the Manchester system, you realize that we had 2 colpostats at the 2 lateral vagina furnaces, and 1 placed right up to the cervical os. But when you look at the Manchester system, it had 2 colpostats placed at the 2 vagina furnaces, separated by a spacer. This spacer was between 1 cm to 1.5 cm in length, and the intrauterine tube had 3 radium tubes in it. And so you could clearly see how remarkably similar the design of the Manchester applicators were very similar to the Paris applicators. As a matter of fact, this was derived from the Paris system. And so when you look at the Manchester system, it had a pair of ovoids and 1 intrauterine tubes of 3 lengths, 2 cm, you have 4 cm and 6 cm. And the ovoids were designed of different sizes. You had 2 cm, 2.5 cm, and you had 3 cm. Now, the spacer that was placed between the ovoids had a length of 1 cm to 1.5 cm. Now keep in mind that the largest ovoid was placed in the most roomiest part of the vagina. The loading system for the Manchester system was kind of interesting. Essentially, the treatment was defined in terms of dose to a point that was representative of the target and which was anatomically comparable from one patient to another. And the dose was defined in terms of unit, in which 1 unit was equivalent to 2.5 milligrams of radium filtered by 1 millimeter of platinum. Now, keep in mind that all the loading of the intrauterine tube and the ovoids were made in terms of integral multiples of this unit. And so for the intrauterine tube, you have the short 2, medium 4, long 6 centimeters, and the short had 8 units, and 8 multiplied by 2.5 will give you 20 milligrams of radium, and you could clearly see the loading pattern. Now the ovoids, you have the small, which is 2 cm, the medium 2.5, and the large 3 cm. And the small was loaded with 7 units. 7 times 2.5 will give us 17.5 milligrams of radium. And the large ovoid was loaded with 9 units, and so 9 multiplied by 2.5 will give us 22.5 milligrams of radium. And so the amount of radium that was prescribed was a function of the size of the ovoid and the length of the intrauterine tube that was used for that particular patient. One of the things about the Manchester system that really has been transferred to modern brachytherapy has been the use of point A, point B, the bladder, and the rectal point. And so the Manchester system essentially can be characterized by the dose to 4 important points. You have point A, point B, the bladder point, and the rectal dose point. Now point A is defined by 2 centimeters superior, just right above the cervical os, and 2 centimeters from the central channel or from the intrauterine tube. And so this defines point A. This is 2 cm, and this is 2 cm. Point B is 5 cm lateral at the level of point A to the mid-pelvis. Now the bladder point, as you will later on see, is defined to be the most dependent portion, of the Foley balloon that is filled with 7 cc's of contrast. And the rectal point is defined as 5 millimeters posterior to the posterior vaginal mucosa at the lower end of the intrauterine source or the mid-vaginal source. Now, what you need to keep in mind that in modern brachytherapy, the definition of point A has changed a little bit, has been modified. But point A is a dose limiting point and defined as 2 cm lateral from the central uterine channel and 2 cm superior of the mucosal membrane of the lateral fornix at the plane of the uterus. Point B is 5 cm lateral to the midline and 2 cm above the cervical os, and is actually used to characterize the lateral spread of dose. What I want to mention on this slide is the fact that point A is a dose limiting point that is defined to be the point where the uterine vessels cross the urethra, and it was found out, or it was determined, that the radiation tolerance of the structures around this region was essentially the main limiting factor in irradiating the uterine cervix. Point B is intended to be representative of the pelvic's lymph node dose, and hence its definition is typically relative to the patient's midline rather than to the tandem's midline. Now, on this slide, essentially we're looking at the tandem and ovoids, and point A is redefined to be 2 cm superior to the external cervical os and 2 cm lateral to the cervical canal, as you can clearly see. Point A, keep in mind, the dose at point A correlates with the local tumor control as well as the incidence of late normal tissue toxicity in the pelvic region. Point B dosimetrically is used to characterize the lateral dose spread and represent the dose to the pelvic wall near the obligator lymph nodes. Now, one of the fundamental difference between point A and point B is the fact that point A is defined relative to the applicator, while point B is defined relative to the patient's midline. What that implies is that if the tandem is displaced or if the intrauterine tube is displaced, point A will move with the tandem, but point B will remain fixed at 5 cm with respect to the patient's midline. Now, the point A, for a tandem and cylinder, point A is defined as 2 cm above the flange and 2 cm away from the central midline. For a tandem and ring, point A is defined to be 2 cm above a line drawn from the most lateral positions and 2 cm away from the midline of the tandem. One of the things that is talked about in this report is the absorbed dose pattern in brachytherapy and how fundamentally it's different from the dose pattern in external beam radiation therapy. Now, typically in external beam radiation therapy, the dose is prescribed to be uniform within the target and falls, gradually in the penumbral region outside of the target. But in brachytherapy, the dose is typically maximum adjacent to the source and falls continuously and rapidly, following the inverse square law away from the brachytherapy source. Hence, this implies that the treatment volume essentially cannot be depicted with the use of isodose curves. As you can clearly see in this graph, the dose adjacent to the source is the highest, and it falls rapidly and continuously as you move away from the brachytherapy source. So this explains the dotted line for brachytherapy case. But for external beam, the dose is typically uniform within the target and then begins to fall off gradually and then rapidly in the penumbral region outside of the target. And so the definition of relevant volumes, the target volume is defined as the volume that contains the tissue to be irradiated to the prescribed dose. The treatment volume is defined as the volume enclosed by the relevant isodose surface and at least engulfs or encompasses the target volume. The reference volume, in which it's one of the parameters recommended by this report to be reported, is defined as the volume enclosed by the reference isodose surface. This typically facilitates intercomparison between centers. And the irradiated volume is defined as any volume that is larger than the treatment volume that receives a significant dose or a dose significant to the surrounding organs at risk. And so, as stated, this report actually mentioned the fact that it is often brachytherapy is given as a boost to external radiation therapy. And if this is the case, and if both are planned from CT scan, then the dose can actually be overlaid. In other words, we could do a planned sum and look at this critically to ensure that the constraint to the normal structures are met before the patient is actually treated. And so this brings us to an important question. How can we specify a radioactive source? In other words, how is the strength of a clinical brachytherapy source be determined? This report recommends that we can specify the strength of a brachytherapy source using two physical quantities. One is the reference air kerma rate, and the second is the total reference air kerma tract. Now, the reference air kerma rate is essentially the air kerma rate to air in air at a reference distance of 1 meter from the source, corrected for both attenuation and scatter, while on the other hand, the total reference air kerma tract is essentially defined as the product of the air kerma rate of all the brachytherapy sources in all the channels with their respective channel times. In other words, it is the sum of the reference air kerma rate and the duration of the application of each brachytherapy source used. Now, the second part of this presentation, we are going to talk about the recommendations for reporting absorbed doses and volumes in intracavitary brachytherapy. And so this report for reporting recommends that we should describe the technique used, the time dose pattern, in other words, the application duration, the total reference air kerma, provide a description of the reference volume, the absorbed dose at the reference point, and the recommended reference points includes the bladder reference point, the rectal reference point, the lymphatic trapezoid, which we're going to talk about, and the pelvic wall reference point. The pelvic wall reference point. Now, in the description of the technique, the report essentially recommends that the technique should be described, one, by stating the source in terms of the radionuclide that is used, the reference air kerma rate, the shape and the filtration of the source. And so in order to describe, in order to provide a description of the source, we need to provide the type of radionuclide that is used, or the radioisotope that is used, the reference air kerma rate of the source, the shape as well as the filtration used, whether is it 1 millimeter of plutonium. Secondly, for the simulation of a linear source, is it simulated in terms of a set of point sources, or is it simulated with the use of a moving point source? And if it is a moving point source, what is the type of motion? Is it continuous? Is it stepwise? Is it unidirectional? As well, with that we need to also state the dwell times in each dwell position of the stepping point source. Thirdly, we need to provide a description of the applicator, or the type of applicator used. In this respect, for a particular application, one, we need to provide the size. For example, if it is a cylinder, we need to provide the length as well as the diameter of the cylinder. And we need to provide the geometry, the rigidity. For example, if it's a tandem and ring, we need to, are the parts fixed or are they loose? The type of shielding material used, the connection, as I said, is it fixed or loose, as well as the curvature of the tandem, in other words, the angle of the tandem, as well as the type of sources. Now, secondly, we need to be able to provide a description of the loading pattern. And so the report talks about reporting the total reference air kerma rate. Now, historically, just briefly, the quantity that was units that was used was milligram hour of radium to specify a particular brachytherapy source, in this case, which was radium-226. Now, when new radioactive sources or substitute were brought into the market, then a new unit was proposed that was called the milligram hour radium equivalent that was used for non-radium sources. But Report 38 recommends the use of TREC, the total reference air kerma, which essentially is a measure of the total dose received by the patient in the duration of treatment. In other words, the total reference air kerma TREC, which is defined as the sum of the product of the reference air kerma rate and the irradiation time for each source, is directly proportional to the integral dose given to the patient. And the next thing recommended by the report is to provide a description of the reference volume. Now, the reference volume essentially is defined as the volume encompassed by the reference isodose surface, which was typically defined in this report by a dose level of 60 gray, or encompassed by the 60 gray isodose surface. But if it was not encompassed by the 60 gray isodose surface, then the reference volume needed to be calculated, and the reference volume was given by the height, the width, and the thickness which how to calculate this was provided by this slide. Keep in mind that the height is essentially the maximum dimensions along the intrauterine source and measured in the oblique frontal plane containing the source. The width dW is the maximum dimensions perpendicular to the source and measured in the oblique frontal plane, and the thickness is the maximum dimensions perpendicular to the source and measured in the oblique sagittal plane right here. And so this report recommends that we should state the absorbed dose at 4 important reference points. You have the bladder and the rectal point, you have the lymphatic trapezoid and the pelvic wall reference point. Now, the maximum dose to the bladder and rectum essentially depends on the distribution of sources within the applicator, and it is recommended that the maximum dose at this point should be less than 80% of the prescribed dose at point A. Point A is a dose limiting point. We talked about this in details earlier. Now, reference points that are closer to the source typically are inappropriate in characterizing or specifying the dose, as they are located in a high gradient region. And because they are located in a high gradient region, any slight change in the position of the applicator will drastically change the dose at this particular point, and so they are not really recommended points for dose specification. Now, the bladder reference point is defined using a Foley catheter to fill a Foley balloon with 7 cc's of contrast, and the bladder reference point is defined at the posterior aspect of a Foley balloon which has been filled with 7 cc's of contrast, as shown in this diagram. You can clearly see in this radiograph the Foley balloon and this right here is the bladder point at the bottom of the Foley bulb. Now on the other hand, the rectal reference point is defined, is located 5 millimeters. It's located 5 millimeters posterior to the vaginal wall in the lateral radiograph, somewhere around here, and it's also indicated on this slide right there. Now the reference points with respect to the pelvic's bony anatomy are the lymphatic trapezoid and the pelvic's wall reference point. Now keep in mind that the lymphatic trapezoid essentially represent the doors at the lower para-aortic common and the external iliac lymph nodes. In order to draw the lymphatic trapezoid, a line is drawn from the level of S1 and S2 junction in the sacrum to the top of the pubic symphysis. Then a line is drawn from the middle of this line right up to the level of L4, or to the anterior aspect of L4, and this essentially forms a trapezoid, and this is called the lymphatic trapezoid. And lastly, the reference point recommended in this report is the pelvic wall reference point. Now the pelvic wall reference point essentially can be visualized in an AP or lateral radiograph, and is typically related to the fixed bony anatomy around the pelvis region. Now the pelvic wall reference point essentially represents the doors at the level of the distal part of the parametrium and the obligator lymph node. As you can clearly see, in order to determine the pelvic wall reference point, a line is drawn perpendicular to the highest point of the acetabellum and parallel to the inner aspect of the acetabellum. When the two lines meet, this forms the right pelvic point, and we do the same on the left to form the left pelvic point. Now remember that the dose at this point represent the absorbed dose at the distal part of the parametrium and the obligator lymph nodes. And so thank you so much for staying with me for this presentation. Keep in mind that this report essentially recommends 5 things: the description of the technique used, the applicator duration or the time dose pattern, the total reference air kerma or TREC, the description of the reference volume, the absorbed dose at reference point, that is the bladder reference point, the rectal reference point, the lymphatic trapezoid, as well as the pelvic reference point. Thank you so much. I look forward to having you in the next presentation. Stay blessed. Bye bye.